So when you have a substance, it might be nice to know when the solid turns into a liquid, when the liquid turns into a gas. And as we talked about at the beginning, sometimes solids go straight to gases and gas sometimes goes straight to liquid, or gases go straight to solid. So this comes up with the idea then of what's called a phase transition. And a phase transition means you're going from one phase to the other. So you're going from a solid to a liquid, or a gas to a solid. Any combination of those three is possible. When you have a phase transition, it's only possible through understanding kinetic energy and the intermolecular forces. And they're really important. They're around us all the time. If you've seen ice on your car windshield, that's deposition. If you've ever been for a run with a dog or another family member or whatever, that involves sweat, which vaporizes after a while. So these things are pretty important. Now, we're going to be using again the terms endothermic and exothermic. And endothermic means it needs energy to make it happen. Exothermic means energy is released when it happens. And both of those will be important. So the ones on the left are lowest kinetic energy. It also has the strongest intermolecular forces. And of course, that's solids. On the other hand, gases have the highest kinetic energy and almost no intermolecular forces. They're so independent of each other. So knowing how this all comes together, we can start figuring it out. So within the same phase of a substance, you can figure out the energy required by using Q equals mc delta T. And C was the specific heat capacity for the substance. The amount is usually something measured in grams, and delta T will be the final minus the initial change for the substance. So Q equals mc delta T works really well if you keep it in the same phase. So an example, if you were heating water from 25 Celsius to 90 degrees Celsius, you would use mc delta T. Your heat capacity would be 4.184. You'd multiply that by the amount. Your delta T would be final minus initial temperatures, and you'd be good to go. And Q, the sign of it, will tell you if it's exothermic or endothermic. So if you add energy, Q will be positive, endothermic. And if you get energy out, Q will be negative, exothermic. You can also, though, have a phase change, like you can turn a solid into a liquid, you can turn a liquid into a gas, stuff like that. And there's also a heat associated with that can be positive or negative, all right? Q, the value of Q, the amount of energy it's going to take or the amount of energy you're going to get out, depends on the amount times the delta H of a phase change. Now, delta H is enthalpy, and there's lots of different delta H values. So, for example, there's a delta H of vaporization, which gets delta H vap. And if you want to turn that poor chocolate bunny up there into a liquid mess, you're going to have to turn the solid into a liquid. I would believe that's what it's turning into there. There's going to be the amount of the rabbit times some type of delta H for the process, and you can actually figure out Q. Q values, again, will be joules or kilojoules, and as long as you have the right values, you can figure out anything like that you want to. Sometimes you'll see pictures like this, and enthalpy, H, is on the left-hand side. So that's the Y energy axis. And they can be kind of confusing, but here's the general idea. Anytime you go from a solid to a liquid to a gas, or if you go directly from a solid to a gas, endothermic. It's going to be a positive energy value. You're going to need to put energy in. So if you look at the up-hand left arrows there on the left side, the biggest one, sublimation, that's the energy to go from a solid at the bottom to a gas at the top. It's going to be endothermic, and it's usually a very big number. On the other hand, if you go from a solid to a liquid, that's the melting process. That's an energy, but it will be positive. It'll take energy. Liquids to gas, you have to vaporize the gas, so that's vaporization. So these are the terms that we'll use. Sublimation, solid to gas, melting solid to liquid, vaporization liquid to solid, etc., etc. On the other hand, if you're going from a gas to a liquid to a solid, or from a gas to a solid, those actually give energy off. Those will be negative numbers. So if you look on the right-hand side, the blue arrows, condensation is the energy, the delta H value that goes from a gas to a liquid. Freezing is a delta H value that goes from a liquid to a solid, and deposition is the fancy name for when a gas goes directly to a solid. But the important part for us here is those are all exothermic. The ones on the left are endothermic. You have to put energy in. The other side are exothermic. Now, why this is happening? On the left-hand side, solid to gas, solid to liquid, liquid to gas, you're breaking intermolecular forces. And that's not going to happen just by looking at it. You have to add energy. So all of those are positive to break. You're adding more kinetic energy to break the intermolecular forces. On the right-hand side, if you go from gas to solid, gas to liquid, liquid to solid, then you're going to get energy out because the kinetic energy that those systems had is being gotten rid of and the intermolecular forces start taking over. Those all release energy. So this is important. Solids to liquids, liquids to gas, always endothermic, always going to be positive Qs. Gases to liquid, liquid to solid, always exothermic. Those will always be negative Qs. The Clausius-Clapeyron equation is an equation that's used often to figure out things like the heat of vaporization. It can be used for lots of these different delta H values we're going to talk about, but the delta H vaporization is real common. And so these scientists figured out, which is a testament to their power, if you make a plot of the natural log of pressure, vapor pressure, versus 1 over the Kelvin temperature, you actually end up with a straight line. And if you remember from the graphing lab, this is a kind of problem you can apply a linear regression to. And a linear regression will give you the slope, the y-intercept, and the correlation coefficient. Well, the slope here is the important part. Slope equals minus delta H vaporization over R. And R is the so-called energy R constant, 8.3145 joules per mole Kelvin. So this is a great way to find delta H of vaporization if you have lots of values. Now, if you only have 2 values, you can use this equation right here. It's not as good of a method as plotting natural log of vapor pressure versus 1 over temperature for lots of different points. But if you only have 2 values, this will work. You can get a delta H vaporization out that way. So this is how these numbers come around. We probably won't do a lot with this because it's kind of crazy, but it is something you can do. All right, you'll take the natural log of vapor pressure, plot 1 over the Kelvin temperature, and be good to go. Now, we can use those heats of vaporization and other delta H terms, as well as Q equals mc delta T, in problems like this. So let's say that the scientist wants to know the quantity of heat in kilojoules that's required to melt 500 grams of ice, which is at 0 degrees Celsius, and heat the liquid water, to steam at 100 degrees Celsius. So we're turning ice at 0 to steam at 100, all right? And to solve this problem, we need to basically have 3 steps. And I'm going to show you on the graph here. First of all, we're starting at ice at 0 degrees Celsius. And the first part we're going to do, I'll call it number 1, we're going to melt the ice. We're going to turn that ice into a liquid. That's going to be the mass of the object times one of those delta H things. And that's going to allow us to calculate Q, the energy required. And then the second part is on this kind of diagonal line right here. That's going to be the energy required to take the liquid water at 0 Celsius and turn it to liquid water at 100 Celsius. So number 2 is going to be Q equals mc delta T. We'll use the mass of water times 4.184, the specific heat capacity, times the delta T, which will be 100 minus 0, to figure out what that value is going to be. And then finally, step 3, we're going to take that liquid water at 100 degrees and we're going to turn it into steam at 100 degrees. So we're going to use the mass of the object times some type of delta H vaporization, which is the energy required to vaporize it, to figure out the Q part there. So we're going to have 3 calculations, step 1, 2, and 3. They're all going to be positive numbers because we're turning a solid into a gas. That's always an endothermic, always positive numbers. And it's not too bad. Just make sure that you break this down into separate sections and then add those results all at the very end. A couple of things. Temperature is a constant while the ice melts. So temperature, you can see, is on the y-axis right there, and you can see I'll highlight it in blue. That part is totally flat. So you're not changing the temperature as you melt the ice, all right? That's why that part, when you have a phase change, it's the mass of something times the delta H of that quantity, all right? But there's no temperature component in that part right there. When you heat the water, this part right here, you do have a temperature change. You're going from 0 Celsius to 100 Celsius. Your delta T, which can be in Celsius or Kelvin, I would definitely use Celsius here, will be 100. We'll use the specific heat capacity for liquid water, 4.184, which I really want you to know / memorize, and we'll multiply it by the mass to get then that value. And then the final part here, where we're evaporating the water, which I kind of circled over part of it, sorry about that. You can see again, there's no temperature change, all right? We are literally turning the liquid molecules into gas molecules. We're breaking the intermolecular forces in the liquid and turning it into gas, which has no intermolecular forces. So it's a whole different environment. Now, the length of those lines will be proportional to the energy, and you can see that the green line is a lot longer than the purple or the blue lines, so that's probably going to be the biggest of our calculation numbers here, as we'll see. But at the very end of this problem, we'll add the amounts from the blue, the purple, and the green together to get the overall energy. No problem. We will need some constants to figure out this problem. Now, the specific heat of liquid water, again, is something I'd like you to know, 4.184 joules per gram Kelvin. But here are two other numbers we'll need, and I would always give you these numbers, by the way. The delta H of fusion, the enthalpy of fusion, sometimes called heat of fusion, for ice is 333 joules per gram. So what that says is that 1 gram of ice is going to require 333 joules to turn solid into liquid. The heat of vaporization, delta H vap, is 2260 joules per gram. So every gram of liquid water needs 2260 joules to turn it into a gas. So notice it's quite a bit more energy to turn liquids into gas than it is solids into liquids. Just kind of an interesting phenomenon. To do this problem, we have the mass, 500 grams of ice, and that mass is going to stay constant as we turn it into a liquid and a gas. It's not going to change. We're starting with ice at 0 Celsius, and we're turning it to steam at 100. So the first thing we're going to do is we're going to figure out the energy required to melt the ice. We'll use the heat of fusion. So the amount times the delta H of fusion will be 500 grams times 333 joules per gram, 1.67 times 10 to the 5th joules are required to melt the ice at 0 Celsius. Step 2, we're going to raise the water from 0 Celsius to 100 Celsius. This will be Q equals MC delta T. So the C value is 4.184. The mass is still 500 grams. Delta T can be Celsius or Kelvin. It doesn't matter. It's going to be delta T of 100 either way. 2.09 times 10 to the 5th joules. And then the final step will be to evaporate the water. We'll have the amount, again, times the delta H of vaporization in this case, 500 grams times that 2260 joules per gram value, 1.13 times 10 to the 6th joules. So the final step, we're going to add the 1.67 times 10 to the 5th number to the 2.09 times 10 to the 5th number, and add that to the 1.13 times 10 to the 6th number. Add those up, you get 1.51 times 10 to the 6th joules. If you divide that by 1,000, you get kilojoules, 1,510 kilojoules. And that is the energy required to melt 500 grams of ice and turn it into steam at 100 degrees Celsius. Notice it's a positive number, it's endothermic. This isn't going to happen by itself. You must add energy to make this happen. Another kind of fun thing, if you wanted to turn the 100 grams of steam at 100 degrees Celsius to ice at 0 degrees Celsius, and it was the same 500 gram amount, the overall energy would be the opposite sign of what we just calculated. So turning the gas into a solid again, you would get out negative 1,510 kilojoules. It's the same process, just reversed. You can do that with these Q and delta H signs. Kind of cool.